It's a pleasure to have Karen Prestegaard with us today. She got her PhD in geology and hydrology from UC Berkeley, and she currently holds a faculty position at the University of Maryland, College Park in the geology department. But importantly, she's been investigating a number of different areas that are relevant to our concerns here in the county, among them stream flow generation and their variations with the watershed scale, as well as how they vary with geology and land use, and most importantly, maybe for us, how what the consequences are due to climate change.
Thank you, Joanne. So I'm going to start off by saying I'm going to talk about the research I've been doing in Frederick County, but also adjacent areas like down near Silver Spring here, that inform on how we can look at some of the issues up near Frederick as well. So pulling together information from other adjacent regions. The other thing is that I decided not to pull up all the information and try to synthesize it about what are the stressors being in place by rates of water withdrawal in different places, because I want to talk primarily on how climate and land use are changing. And then the next thing to overprint on top of that is how are people using the water, at what rates are they using the water, and what are the new proposals that are going to put these stresses. So the human stressors, in addition to things like land use change. So land use change really affects the hydrology, as you can see on this image here, with all the purples and reds for the urbanized areas and the urbanized corridors going out along the main roadways, and then in between the nice green mountaintops following the Catoctin and other areas. So I'm going to talk about what's happening. So I'm going to talk about precipitation, floods, and how they're changing and what the kinds of events they're responding to. And I'm also going to talk about drought conditions and what drought conditions are responding to and what we know and don't know about them. So if we just look at the annual precipitation in Frederick, it looks pretty boring. You see a nice big dip in precipitation during the big Dust Bowl era of the 1930s. You see the 2018-19 flood year being an above average year up in Frederick. And you can see some other years going back in time, 1972 Hurricane Agnes, the 1996 Hurricane Fran. So a big flood or a big precipitation event usually pops the annual precipitation about a standard deviation above the mean. So you can see the big events in the series. But what you don't see is, yeah, it's getting drier. You can see that it's possibly getting wetter, but it's definitely not getting drier. And that's consistent with what you might expect with a warming climate, where more water vapor is put into the atmosphere and more is coming in from the oceans. And you can see that the mean annual temperature, again, shows a mild increases over time and fewer of the lows that we've had in the past. So this is also consistent with what we know about warming in this region, where the winter temperatures and the nighttime temperatures in particular are getting warmer. Okay, so one of the big stressors on everything is the increasing amounts of urbanization, which some people visualize as sort of cancerous growths coming out from the coast. And I guess in diagrams like this is maybe what it looks like. Again, you're seeing the green for the forested mountains and the reds and the purples for the urban area here in Baltimore. And then the connecting roads are getting little communities strung along them. And then as we get to the Frederick Valley. So the topography, the type of bedrock, will be a story in how the landscape responds. So the issues that I want to talk about that are associated with land use and climate change is what's happening to the extremes. So what I just showed you is changes in annual temperature and annual precipitation. The big changes are likely happening at the extreme ends, the storm events, and in particular, we want to look at what storm events seem to be changing the most, and therefore what kinds of streams are going to respond to that, and also periods of time without precipitation, which can generate droughts. And also even without climate change, urbanization has big effects on the hydrologic processes. In particular, it increases the magnitude of peaks as more stormwater runs off from impervious cover. And also because less water infiltrates, there tends to be lower base flows as well. So I'll address that as well. But before I get there, I want to talk about the storm types and size and duration that are common in the Frederick area. Some of them are becoming less common, some of them are becoming more common. So we're in a region that gets tropical storms and hurricanes in the summer, particularly late summer, early fall. Typically, September is our peak opportunity for getting tropical storms and tropical storms and hurricanes trundling into the area. And they're actually pretty important hydrologically because we have low flow conditions in streams in the late summer because of evapotranspirative drawdown. And so the tropical storm activity in the fall frequently is one of the first things that starts to recharge the systems. And multiple years without any tropical storms at all has actually kind of shifted that pattern. And I'll show you that later today. We also have thunderstorms. We had some really big thunderstorms that hit Maryland early part of August this year, which is one of the wettest parts of this past summer. And also we have winter storms, possibly fewer of them than we used to have. But also we get snow and rain on snow, which then melts the previous snow. And those events in particular can create some localized flooding in the Catoctin and adjacent regions. Okay, so just to show the hurricane tracks, these are all the hurricanes that have, and tropical storms and tropical depressions that have tracked in and near the state of Maryland. You can see that most of them are clustering along the coast. In fact, it's only tropical storms and tropical depressions for the most part that have made it to the more central part of the states where Frederick is. That doesn't mean that they don't dump a huge amount of rainfall, because it doesn't have to be a hurricane, which is defined only by the wind conditions, to dump a whole lot of rain. And we've seen that the last couple of years. If you paid some attention to what was happening in the Gulf with Hurricane Harvey and then Hurricane Beryl earlier this year that hit the Houston region, and those big hurricanes had stalled out as they got to Houston, and just down the winds disappeared a little bit, but the storm itself hung around and dumped up to 60 inches in some places in parts of Houston. So having it decrease from a hurricane to a tropical storm doesn't necessarily decrease the chances of flooding, and we'll see some of that. So almost when we look at the flood frequency characteristics for the Monocacy River, we have a series of winter storms and thunderstorms in the lower part of the distribution. Between 1 and 10-year recurrenceable storms are primarily thunderstorms and winter storms. And then there's a series of much bigger storm events, which are the tropical storms and hurricanes. And the largest one on record for the Monocacy is still 1972 Hurricane Agnes.
Yeah.
When we look at the flood maps for, what's wrong with this? Flood maps for the city of Frederick, the big storms cover large spatial areas, and they create flooding on the big rivers, which includes the Monocacy River itself. A lot of the original flood mapping for the Monocacy River, they used the 1972 flood levels and been modifying it since then. But you also see flooding along these smaller tributaries that are entering into downtown Frederick. And that's where a lot of the flooding that's currently, and also this direction, some of these smaller tributaries are actually the ones that are impacting buildings in the Frederick area. So when we look at what affects the smaller tributaries can be affected by tropical storms and hurricanes as well, but the intensity of storms is much higher with the smaller duration storms. So a thunderstorm on the average has much higher rainfall intensity than a much longer duration storm, even something like a hurricane. And so you can see one of these short duration storms, this is actually a big thunderstorm, the ones that hit Ellicott City, they're very similar to the ones that hit Frederick in 2018. These were 3-hour in durations. They covered a fairly small spatial area. They didn't even get much into Baltimore, didn't get down into Laurel, didn't get over into Frederick. The storms that hit Frederick in 2018 were different than the ones that hit Ellicott City. They were later in the year. And you also see, in general, these short 3-hour storms tend to occur not as winter storms, but as summer, June, July, August, and dropping off in September and October. So you can see that these are hitting at the warmest time of the year when there's a lot of moisture in the atmosphere that can really get advected into places. So these are the storms you've been hearing about. This is very similar to what hit in Spain, a short duration, high intensity event. It's what hit in Tennessee a few years ago. And we've been seeing these pop off in temperate areas really around the world. So that is something worth looking at, because when we look at what the probable storms are in an area, we think about them in terms of what's the duration of the storm. And the reason that we think about duration is going back to this diagram. The big storms cover a large spatial area, so it's going to take them a long time to cross over a region. So a hurricane is often a 24 or 48-hour storm. A thunderstorm can be a 1-hour storm or a 2-hour storm or a 3-hour storm, usually not a whole lot longer than that. And as a result, when we look at the intensity and the amount of rainfall that falls with different storm events, we break those storm events up by their duration. So the 3-hour storm that hit Frederick in May 15th, 2018, for example, had about 6 inches of precipitation. It lasted about 3 hours. And you can see where this fits on an intensity, duration, frequency graph. So this is the amount of rainfall. This is the storm duration in hours. And that upper line on here is the 100-year storm. So when people look at that storm, or they look at the one that was in Ellicott City, they go, okay, that's a 1,000-year event. And this is where people are really questioning what's going on with the amount of moisture in the atmosphere and how that's changing. There's another way of looking at that is to look at the storm duration, the intensity in terms of inches per hour. And this is the same storm plotted as a 3-hour duration event. And the average intensity over that 3 hours was 2 inches an hour, because it was 6 inches total. And you can see that it falls significantly above the 100-year storm there. Sorry, you had a question?
No.
Okay, so it falls significantly above that 100-year storm, but you can also look over and see that there's smaller duration storms that easily have that intensity. So when we look at these storms and people say, oh, it's a 1,000-year storm, they can also look back at this and say, I think something else is happening. I'm thinking that why this is automatically changing, the amount of water vapor that can actually be dumped in a 3-hour storm is now more equivalent to what could be dumped in something like a 2-hour storm, because of the water holding the water vapor in the atmosphere is actually higher, and its connection to the ocean and bringing these storms on shore is sometimes a better connection. And we see that with things like the atmospheric rivers, which are becoming more common in California. And also some people think that the event that happened in Ellicott City was an atmospheric river. But it's not unprecedented in terms of the actual intensity. It's just not what we expected for that duration of the storm event. So if we look at the floods that are generated by these short duration thunderstorm types of events, which seem to be the ones that we see increasing in frequency. So these types of storms have occurred in the past. This is a paper by Ed Doheny and Nealon, from both people at the USGS. It's a recent paper, and they just took the previous data on these big storms. So August and September of 1971, there were some storms like this. And then in Ellicott City in 2018 and 2016, there were storms. And then when they plotted those, the 2016, 2018 storms were significantly bigger, but not hugely bigger. You can see them here in the red squares. And then all of the largest ones were up here from the previous 1971 storms, and then the whole region also had that. The other thing you can see is that the discharge generated, this flood data, the discharge generated in the streams by these intense storms rapidly decreased with the drainage basin area. And that's for two reasons. One is the floodplains and other features that attenuate or slow down the flow, often by flow resistance and channel resistance, and the fact that tributaries come in at different times. And the other reason is that the intensity of the storm is just focused over a smaller spatial scale. And so by the time you get to the larger basin areas, there aren't even any storm flood events to plot, because it just stuck with the smaller basin areas, about 100 square miles or smaller. And so that means when you look at Frederick, you don't see these 3-hour storm events as creating a giant peak on the whole watershed. But if you look at how streams are organized in the Frederick Valley, you've got the Frederick Valley, which is underlain mainly by limestones, and it's a valley. And you've got the steep tributaries that are short, shallow depths to bedrock, and short path lengths, which means they can deliver runoff quickly. On the positive side, though, most of that area is currently forested, so that the land use is not impacting a lot of these areas in terms of increasing the amount of runoff that they're bringing. But these are susceptible to these short duration intense storms. We also see slightly longer storms on the other side of the valley, and again, a fair bit more urbanization on the other side, where these small tributaries are bringing in runoff. In addition to the FEMA maps, the First Street Foundation has been going around and looking at a lot of urban areas and trying to map out flood hazards in these areas. And recently, a lot of their maps have been matching where people are losing homes and lives and other things. And one of the reasons for this is the Flood Street Foundation, or the First Street Foundation, is paying attention to these small tributaries. So the bar on the bottom there is the flood depth, and the blues, the different colored blues, are how deep the floods would be. And you can see up in the headwaters of the tributary, they're tributaries, they're not going to be very deep. And this is the amount of overbank flooding that's going to occur. So it could only be like maybe a half a foot or a foot, and then deepens to a couple of feet as it goes downstream. This is with the current land use. So as land use changes, some of these places could have much higher floods coming down them. So you can see all along here, the generation of floods along these small tributaries, particularly along this side, on the Catoctin side, because they're steep and the depth to the bedrock is relatively shallow. So I'm showing some of that here. This is the topography on the Catoctin side of the Frederick Valley. And then you get over on this side, you get over into the Piedmont and the Frederick Valley syncline here. So this is all these underlying pink colors here, and the blue colors are the limestone, and that's fairly permeable material. So as the flows come off of the kind of steep mountainsides here, they actually have things to infiltrate into if that part of the landscape isn't built up. So you can sort of see where I'm going here in terms of of where we might want to look at what's happening in terms of where development pressures are, where the streams are probably going to have the biggest changes in flood magnitudes. And I'll show you some data that we've collected that demonstrates that. So I haven't been collecting data on those small tributaries in the Frederick area. They are currently ungauged. There's one gauged up in Carroll Creek in the Frederick area, up here somewhere. And the USGS, one of my former students, actually did a nice study of surface groundwater interactions up in the Carroll Creek area, which I'll send to you guys, because you should get Peter Goodling to talk about that, because it's a very nice study of what's going on there. But he was mainly working on the area right around Fort Detrick to look at surface groundwater interactions and groundwater contamination associated with Fort Detrick. And also the contributing streams were primarily forested. So as you get down towards Frederick more, some of these contributing streams now are in the urbanized kind of suburbs of Frederick, heading up the mountainsides there. So I looked at a fairly similar setting in the area around Silver Spring, Maryland, with my graduate student, John Harris. And in this area, the uplands were actually what's urbanized, and the area near the streams a little bit steeper, and the depth to the bedrock near the streams is relatively shallow. So this is a little bit of an inverse of what you see in the Frederick area. In the Frederick area, the hill slopes are steep and the valleys flatten out because they're underlain by that limestone, which means runoff from the uplands could potentially infiltrate into the limestone and the soils in the Frederick Valley, if it's able to, if there's enough room for infiltration and not too much impervious cover. So in the Silver Spring area, we looked at the regions with two different types of depth to bedrock. So we looked at the stream here in Northwest Branch. There's a major nick point along it, and that changes the profiles of the river. So I'm going to show you the relationship between the river profile and how steep the river is, and how shallow the depth of bedrock is, and how the rivers respond to urbanization. Because this is a similar kind of problem that I think you're going to be facing in these areas on the edge of Frederick, with whatever kind of development along all of these small streams that contribute to the Frederick Valley that could dump more water into the Frederick Valley. So here are all these small little tributaries that we gauged, and they're, small little tributaries coming down steep hill slopes with not much depth to bedrock, kind of like at Catoctin. We found above the nick point here, which is just the nick point is the stream has propagated upstream as base level drop. There's a waterfall like that you see at Great Falls. There's a little waterfall on this river. There's a little waterfall on most of these rivers. That's why they're called fall zone streams. And above that waterfall, the little tributaries tend to have lower gradient stream profiles, and below it, since the stream is incised downward below the waterfall and it's incised into bedrock, there's a shallow depth to bedrock and very steep convex tributaries. And this steepness index that we calculate using the stream profile and the relationship to basin area ends up being fairly diagnostic in how the stream is going to respond to the effects of urbanization. So here's a little watershed, a little tiny stream channel. Doesn't look like much at all in between storm events. During storm events, big storm events, water will come down here and create a new channel, and then the hill slope soil will fill it back in again. So those are these channels down here. And then the urbanized ones have much higher discharge. So these little sort of side slope, steep slope channels with high steepness indices really can be affected by urbanization. So if they're not urbanized, if they're forested, they don't have much runoff at all. But if they're urbanized, the amount of storm runoff increases by almost an order of magnitude. And this is the kind of thing that I'm envisioning for that west side of the Frederick Valley. What happens when urbanization kind of creeps its way upstream in some of those tributaries? Okay, the flip side of you know, changes in precipitation is that changes in precipitation, if we're not seeing a big change in annual precipitation, that might be because we're getting the same amount of precipitation every year, but more of it is coming down in maybe intense thunderstorms. And then there's maybe gaps between those storms that are long enough that actually create drought-like conditions. So you can see the current stream flow. This is today's stream flow in the United States. If you looked at this map 2 weeks ago, the entire East Coast here was very, very dry. Now it's just the northeastern part of the United States that hasn't gotten any precipitation. We got a little bit, but we're still pretty dry as well in most of Maryland. If you go back over the summer, you can see that technically we're in a significant drought, well, a moderate drought throughout most of Maryland, and a quite significant to extreme drought in parts of the mountains just to the west of you there in Frederick. So back looking at the annual precipitation, again, annual precipitation increasing doesn't tell you anything about, well, it tells you a little bit about drought probability because, you know, we're not back in a hole like we were in 1930. But you could have some big storm events that last very brief periods of time and then big gaps between those storm events. So another thing that my students and I have been doing is, instead of just looking at precipitation totals, we're also, and the magnitude of storms, we're also looking at the magnitude of gaps. So this is essentially a probability distribution of the gaps between rain events. This is the number of instances, the number of gaps, and this is a 1 day gap, which is a pretty common event because it often rains more than 1 day in a row. But then as you get to longer and longer gaps, there's this kind of long tail on this distribution, so that there are periods of time when there's fairly long gaps. We just had a 37 or 42 day gap in precipitation in this part of Maryland when it didn't rain for the entire month of October and a little bit into November. So we can see that these kinds of gaps these were recorded a couple of years ago. So we've even repeated one of the longer gap lengths recently. So if we look at the distribution of gaps, so we mapped out this gappiness for the entire United States. Yeah. And not surprisingly, the Western United States, you know, it has a big gap because it's a very seasonal precipitation in those climates, the Mediterranean climates, where the prevailing westerlies bring in the precipitation, but there's land over here that's not allowing precipitation to come in from the other direction. The summer precipitation is primarily coming up from the Gulf and coming from the Atlantic in along the East Coast. So we get precipitation pretty much all year round, and it rains on the average every 7 to 10 days. So it's pretty much non-seasonal. We get pretty close to zero in terms of the distribution here, meaning it's well distributed. But if we look at the recent changes in this gappiness, we looked at the decade 2010 to 2020 to check to see if it was gappier than the decade before that, and we saw a significant increase in the gappiness essentially from Maryland to the south, and an increase in the gappiness to the an increase in gappiness to the south and a decrease in gappiness to the north. And that is consistent with what USGS found with higher low flows to the north. So it's the 7-day low flow, and it's trending upward in the northeast and downwards in the southeast. Now, this could be absolutely nothing to do with gappiness. This could just be higher temperatures and higher evapotranspiration. It could also be lower humidity. The combination of high temperatures and slightly lower humidity can give much higher evapotranspiration rates. The other thing is that it doesn't take much of a gap in precipitation to lead to a significant drought that affects vegetation. So this is something that Otkin and others have been looking at just the last decade or so, that the onset of a very hot, dry condition can change the drought index, which is what I was just showing you, from not being in a drought into drought conditions in just a few weeks, basically. And then that can continue with more normal precipitation, so it's hard to get out of those kind of droughts. You can also have this intensification during an existing drought, and then again, it goes into a continued drought event. And it's really this hotter temperatures and lower vapor pressure difference that's driving these. And you might have heard about this, that they're talking about in the West, that the droughts are no longer just absence of precipitation. They are related to the hotter temperatures and the much faster drying out of the landscape. So this is a real issue. And we thought that it wasn't going to hit the East Coast as much as it's been hitting the West Coast, but we've been a little concerned the last few years. So we've been looking at the water balance. So the water balance is precipitation and how that's partitioned into stream runoff, how much water goes up as evapotranspiration, and how much is stored in the ground. So it can either be plus or minus change in storage here. So that storage term is water being put into the ground for storage or water being taken out of the ground. So if we look at monthly runoff here, you can see that in the last few years, so here's the 30-year average of precipitation, here's the 30-year average of stream flow. So you see a higher stream flow in the early spring, and then it comes back up again in the fall. The last few years, the last year here, 23, 24, has been quite dry with a little bit of recharge during the winter months. And the 27, 28 period didn't even have that. So these were the years where we didn't have tropical storms or hurricanes in the fall, and we didn't initiate those wet conditions. And when we look at the effects of urbanization, we see that urbanized small watersheds that have thin soils over bedrock, if they are urbanized, they have a lot more runoff. And I didn't show the storage diagrams, but the groundwater storage would be a lot less. So you can see when there's precipitation events in the fall after ET is shutting down, these heavily urbanized watersheds are like just letting that go, particularly if they have thin soils over bedrock. If they have thicker soils, they're retaining that water. So, and if they have thin soils, but they don't have much urbanization, they also retain that water. So this is that response that I was showing you before when we were looking at those. I'm going to pop back to that diagram. This diagram where if you urbanize these steep little watersheds with shallow depth to bedrock, the discharge increases rapidly as an effect of urbanization. So that means that some tributaries are way worse to urbanize than other ones are. And that's sort of where I'm going to end up here. I think that there's a lot of things to examine in the Frederick area. One of the things that we don't know much about is what the role of all of these small tributaries along the two sides of the valley are in terms of contributing water to the valley and to the groundwater recharge systems in the area, and also as urbanization progresses up into the sides of the valley, because it's urbanized a lot of the Frederick Valley itself, what impact that will have on flood events in the area. So this is an area where we're worried both about droughts and about groundwater recharge and about floods. And I think the best handle we have on it, and I think what the USGS and people in Frederick have been working on, is they have a pretty good control of what's happening with the Monocacy River and the flooding, and there's really good plans for that. When we looked at the First Street Foundation and there are issues with the First Street Foundation and its work, but it's correctly pointing out that a lot of the small tributaries are left out of the FEMA flood maps, and we need to consider that, and also the role of what happens with urbanization in shifting runoff around. And it could be that some urbanization could contribute runoff that could be re-infiltrated in some parts of the valley, but not if it's coming from suburban areas into much more urban areas. And it's just dumping water into those urban areas. And I think that's all I have to say.
Kansas?
Would you
Right.
say a little more about why urbanization aggravates flooding?
Well, urbanization, let me see, I'm going to share my slides again and just go to a picture. So this diagram shows this landscape. And you can see in this landscape, there's, you know, all of this is probably suburban lawns and other stuff. It's not open green space. So you've got suburban development. A lot of this is roadways or rooftops or other impervious surfaces. So from those impervious surfaces, two things happen. One is that water has to get to the stream channels by some method, and usually that method it's getting there is by some subsurface pipes or by surface kind of gullies along the way. So there's both impervious cover and then storm sewers that deliver water to the headwater tributaries pretty quickly. And the other thing is that if you've got all this impervious cover in the landscape, water can't infiltrate there. The other thing that we discovered in this particular setting is the uplands in this part of Maryland are the places where the soils are thick, and the hill slopes are where the soils are thin. That's not what you're going to see in, let me quick go back here. Oh, in Frederick, you can see where the kind of the bones of the bedrock are sticking out here. And I've hiked enough around this area that I know that the soils are thin there. In fact, we dragged a ground penetrating radar with us once, and we know that the depth of bedrock is fairly shallow under here. And then the depth to bedrock is deeper when it gets to the valley. So runoff from the uplands here is then going to infiltrate into these areas. So if you urbanize these flatter areas, you are urbanizing the areas where infiltration wants to occur, which is exactly what people did in the Silver Spring area. It just happened that the uplands were the areas that had the biggest infiltration capacity and the biggest amount of storage. So I think the storage, some of the storage that's occurring in these tributaries is probably occurring right along here where the geology is. Flash back and see if I can find the geology here. I put in too many diagrams. Where the geology right along the mountain front here. So you see these colluvial fills, so that's permeable. And this blue limestone there, that's very permeable as well. So those are, water from those little tributaries can come down and then infiltrate here. And that's right where a lot of the pressure is for urbanization, right at the base of the mountain front. Just like, it looks like a good place to build. It's nice and flat and you can dig easily there. And all those are exactly the types of places that infiltration should be occurring. Yeah.
Frederick County is heavily populated with farms, and a drought in the spring is a calamity like last year.
Yeah.
This year it repeated. The
Right.
farmers are suffering. We had this big drought in the October, November. We're indifferent. The crops are done.
Yeah, but that's
That doesn't
that's what you
matter
think.
if
That's
we
what
have
you
a
think.
long
I grew up
drought
on a
now,
farm,
but boy, it was a
and
disaster.
that's not the way this system works. This system works where the recharge happens all winter long. Groundwater tables are at a maximum in the spring, and therefore you need very little rainfall to actually provide enough water in the spring for things to do okay.
But gaps are the disaster when there's no.
Gaps are a disaster, but the gaps in the fall are changing the water balance. And that's in part, if you don't get the recharge in the winter, then you just get more evapotranspiration the following summer. In the summer, the ET is always higher than the precipitation in this region, so that it recovers in the fall from November to April. And the last couple of years, we haven't had the fall big storms. We only had some winter storms, so the recovery was like January, February, or February and March. It wasn't November, December, October and those months. So if you shrink down that recharge season, you're starting every April growing season with a deficit.
Mm-hmm.
And that's what I'm really worried about. That's why I was showing you that pattern. So that the couple of things are happening. The more intensification of the warm weather in the summer they can create those flash droughts. That's bad. But the really dry conditions in the spring that can be a result both of drought in the spring and amplified by the fact that the base flow is already low or the soil moisture is already low because you didn't get the recharge in the fall.
The swing between too much water and not enough water, between floods and droughts.
Yeah.
Well, I like to think that as nature, as climate change's way of teaching us about standard deviations, most people don't understand. And if you look at the numbers, it can hide the fact that the rainfall looks not that
It looks the same,
but it's hiding it.
Yeah.
The question is, does that swing back and forth make the drought worse than it would have been and the flood worse than it would have been because of the constant yin and yang with the environment?
Yeah, it does, because if it's been dry for a while, you notice that the soils get more compacted. And so the infiltration capacities are often lower after a drought, which means more water runs off. So even a dry condition makes the next flood worse. It's not as bad here as it is in, let's say, California, where you get basically hydrophobic soils forming at the surface, but that's neither here nor there. The other thing that happens is that if you get these flood conditions, if you're taking the precipitation and putting it into bigger gaps and more intense storms, the vegetation is having a hard time adapting to that.
Do city and county planners, do they often take into consideration these runoff issues?
Well, they take in consideration what they've learned. So they know that impervious cover is a bad thing, and that they put in stormwater retention ponds, etc. But they don't think, how does impervious cover interact with the underlying geology and geomorphology, which is what we've been looking at. And frankly, we were way more successful than I thought we were going to be in terms of finding things that were actually significant.
Right. Yeah. Well, like in that water element report, they did report on the percentage of impervious cover. It doesn't seem to correlate with the developers, target.
And I have to say that the advent of good GIS has made us stupider in some ways. And the one way it made us stupider is that 1968, when the first people started writing about the effects of urbanization on stream flow and infiltration, one of them was Lynn Leopold, who was my advisor at Berkeley, and he wrote this nice little guide to the effects of urbanization on stream flow, and basically put all the things that I've said. But right at the beginning, they said it's two things. One is the infiltration, the impervious cover that causes more runoff, and then that runoff goes to the street and it goes to a storm sewer and then gets piped out to the flow. So people use impervious cover as the main parameter, and they don't look at things like the channelization and the where those storm sewers go, where they are they going out onto the landscape? Are they going directly to the stream channels? So that connectedness of those pipes is really, really important. Yeah. And then the other one is, what's the depth of bedrock and what's the soil like under there? And they do have soil maps that they take into consideration when they think of where to put a retention pond or something. And they're trying to get away from that kind of thing anyway.
My question is about stream gauges.
Mm-hmm.
I don't understand how they work. What I understand is that they work over time, and that somehow you can figure out groundwater from them.
Well, you could go out every day and measure the discharge in a river and record it. And that would be the best way of doing things. But
What do you mean by discharge?
yeah, discharge is the volume per time. So you'd go out to the river and say, okay, here's the cross-sectional area of the flow, and here's the velocity of the flow. Cross-sectional area times velocity would go feet squared times feet per second, so cubic feet per second. So that would be the flux of water going down the channel. You could measure that every day. That'd be the most accurate way to get it. We're way too lazy to do that, and no one has that much time. So we put in things to record the water level. But the water levels, only tells you the water got up this high. If you measure the cross section, you can kind of estimate what the cross-sectional area is, but you still need the velocity. So you need to go out in the field and measure the whole discharge with velocity meters across the channel. And what we do is record the water level and then make a relationship between water level and the discharge, which is what you actually measured. That's what takes time, is to come up with the rating curve. You can start measuring water level, and then you measure it over a period of time. And as long as you calibrate the relationship between water level and discharge, you've got a lot of information. And that's a real pain in the ass for small streams or any streams. It's a lot of work. So that's what a stream gauger with the USGS does, or what I do with my graduate students on these small streams that the USGS does not want to gauge because they're kind of complicated.
So
Yeah.
would Frederick benefit from more stream gauges?
More is almost always better, but they're expensive. If you want the USGS to gauge a stream, it's $20,000 per gauging station
Wow.
per year.
Wow. Yes.
If you want me to put in a gauging station, it's a grad student and $1,000 to buy the gauge. Yeah.
Are there alternatives that are almost as good but less expensive?
We can put in an automatic gauging station that has a velocity meter on it and a level recorder. You can get one of those for about $20,000, but you don't have to pay it every year.
Okay.
And so if you're gauging for a while, that's not a bad intermediate, unless it gets blown out and then you have to replace it. So you can go with lots of people in the stream, lots of time. A good level recorder, which could be a hobo data logger and some other things, and people in the stream periodically, or the USGS gauge, and they pay professionals to do that. I mean, we're professionals too, but it's not what we're being paid to do. That's the
Right.
difference.
And what about a weather station? Should Frederick have?
Oh God, yeah. So the University of Maryland is putting in finally a University of Maryland or a Maryland mesonet. And mesonets are entire meteorological stations that are going to be set throughout the state. It's gotten harder and harder to get precipitation data from the National Weather Service and NOAA, because they archive it in such strange ways that all of us now use data products like from PRISM. I actually sometimes use a NASA product, so it's a remotely sensed product to get precipitation, because it's just so hard to get the data cleanly out of NOAA, and then there's missing data and you have to fill in missing data. It's kind of weird, but that's the way it is. But the mesonet that the Maryland is going to put in is if you want to see what a really cool mesonet looks like, Google University of Iowa mesonet or Iowa mesonet, and it's fantastic. It'll tell you, everything about, it's got grids throughout the state where they're measuring everything, relative humidity, temperature, everything. And in fact, if I want to make a map of the wind directions for Frederick, Maryland, I go to the University of Iowa or the Iowa mesonet, because they've got a tool there, a toolbox where I can take any wind station in the nation and create a wind row showing all the wind directions. It's so cool.
Wow.
Yeah. And Maryland really wants to do something like that. So they've been putting in, they put one in Clarksburg, they put there's one at the University of Maryland. You guys should say, yeah, we need one at some place. Maybe it should be, further away. I put in my own little rain gauges and they get clogged, and you really need someone that's working on them a fair bit is the problem.
Thank you very much, Karen, for
Yeah.
presenting all these things on the water issues. I certainly learned a bunch.